Hello everyone, welcome back to Chemical Process Design course video with me Anggit Raksajati, and we will continue our second case study about the synthesis of acetone from isopropyl alcohol. And in this video we will talk about the step-by-step simplified simulation. Again, this is a quick preview of the complete flowsheet of the simulation. We've already finished the vapor-liquid equilibrium analysis to get the actual azeotropic composition of the feed. We have already performed some sensitivity analysis for the reactor performance, so now we're ready with the main simulations. Okay, so let's go into HYSYS. Okay, let me continue from my previous file, which is called acetone reactor sensitivity. Now I will save it as a separate file. Let's say acetone simplified. Okay, and I will rearrange my flow sheet so that I have more space for the main simulation. Okay, so I will keep this equilibrium spreadsheet and the Gibbs reactor just in case I will compare the result with the main simulation. Okay, so let's define the fit from the beginning. So I have my feed stream, and then I will have my pump to increase the pressure up until the reactor pressure. And then I will have my mixer to combine the make-up feed with the recycle stream. And then I will have my heater to preheat the feed before it reach the temperature of the reactor conditions. And then I have my reactor. And for reactor, we have already modeled using the Gibbs reactor, and as I told you before, that we get the maximum conversion of about 97.7% at the selected operating conditions, but we will limit round down those number into 90% for the final sizing. And again, I will not directly model using PFR at this stage because it's just too much to do at this point of simulation. I want to finish the closed loop mass balance first, as usual, to prevent any unnecessary risk. Okay, so I will add my conversion reactor. Okay, so I guess that would be enough for now. Let us mix all these things together. Okay, stream 1, let's name it as feed. Okay, I already have it as feed, so let's say it's feed 2. And then the compositions, again, we can get the I guess it's even easier for us to define from stream because we already talked about the feed condition in the previous video, so I will define it from my feed stream. But we have to fix some of those. The temperature is actually not 350, but it's 30 degrees C. The pressure has to be around 1 bar because it's at ambient temperature and pressure. It's in liquid, vapor phase, vapor fraction as 0, composition at azeotropic composition. Okay, same with the previous video. And then I will connect it to my pump. Okay, feed 2, and now pressurized feed, and it's the work of the pump. And as we want to achieve 2 bar at the reactor, so we have to give additional pressure drop for the heat exchanger and the pipeline as well. So I guess I will give it as 3 bar example. Okay, then I will connect it to my mixer. And will be linked to my heater. name it as mix fit. This point, the mix fit is still the same with the pressurized fit because we haven't identified the recycle from the separation. Okay, and then let's connect the preheater. Again, just use a simple heater for now. Later on, you can change it to shell and tube or even perform some heat integration. Let's name it hot fit. Hot fit. Unknown temperature, but we actually already get the number from our sensitivity analysis. It has to be 350 degrees. In terms of the pressure, don't define it as a pressure of the stream directly. I will instead defining my pressure drop. Double click the heater, go to the parameter. So let's just use the default number. Okay, 0.2 bar. Okay, everything looks good. So it's ready to be linked to the reactor. Okay, paper product, liquid product, and because it's isothermal, then that means I have to provide the heat for the reactor. Requires a reaction set. Okay, so and if you check reaction set, we haven't had any option over here because we haven't defined the reaction. So we now must go back to the properties, the reaction. I'll do this quickly because we talked about it in the previous case study. It's a conversion reactor, so I will have to add the conversion reactor instead of a kinetic reactor. Okay, define the component. Propanol. Water is actually an inert. Acetone and hydrogen. Minus as heat. Positive for the product. Wait, it's not minus 2, it's okay. The balance error is 0 now. That means 1 mole of IPA become 1 mole of acetone and 1 mole of hydrogen. And we also know that it is a gas phase reaction. The only reactant is a propanol, so of course the base component would be propanol, and the conversion I'll put 90% based on our sensitivity analysis. It has to be slightly lower, 97% at this selected operating condition. Scale, attach to fluid package, save, go back to simulation, double click. Okay, it's now appears. Unknown duty. Why? And you probably notice over here, because we now add another energy stream into the reactor. Now we have to link with the add another input. Okay, so again, same technique with the Gibbs reactor. We'll put the same temperature for the top product, which is stream 1, so S350. Or even if you want, you can also link it using the set manipulator as described in the previous video. But I will not perform another sensitivity analysis because it is already optimized at the previous video. So let me just directly define those as 350 degrees. Okay, it's ready. Then you can double check the composition of the reactor. Okay, pressure. Okay, now the pressure is actually higher than our initial condition because initially we want to perform at about 2 bar. Okay, so maybe I will add a pressure drop over here because it is still as 0. Let's say that's 0.8 just to round up the number. Okay, so the pressure profile now from 1 to 3 bar plus another 0.2 bar, and then outlet of the reactor we have 2 bar. Okay, or if you want to be more consistent with the feed condition that has to be 2 bar, I think that's also very doable. Okay, so you can go back to the pump. Let's say you want to revise the number, instead of 3 bar, let's just now make the number as 2.2 bar, so that now your heater will still lose another 0.2 bar, so it's sent to the reactor at 2 bar, identical with our case study. I guess that would be better for you, so it's consistent. So now I will update my pressure drop of the reactor. Instead of 0.8, just put a round number, 0.5, this point. Okay, I still have around 0.5 bar left before it reach atmospheric pressure. Okay, check the composition. At stream 1, your top product, you have around 38% of acetone and 38% hydrogen, whereas you have around 4% of IPA. Okay, I guess it's ready to be linked with the next unit of equipment. So I go back to palette, then I will have my mixer just to combine those two outlet together. Okay, so again, remember the block diagram. You can always switch back to previous video or video 2A about the configuration. Now the main idea is to separate the hydrogen first using a single stage separation column. That means I will have to cool down my temperature, because now the temperature is still at 150 degrees C and all of them will still be in vapor phase, superheated one. Okay, so I will decrease the temperature, so most of the compounds will condense while the hydrogen remains in vapor phase. So I'll put my cooler over here. Okay, just press Control. Okay, while you link all this stream together, you want to convert it the old way, the traditional way, I guess that's. So now double click on the cooler, unknown delta P, so let's give another 0.2 bar. Okay, check the pressure, profile pressure. Yes, that's still doable because we still have positive pressure. Now comes the first question. Okay, again, I told you that we have a couple of cooling medium option. Okay, if you want to use a cooling water, that's fine, but that means the temperature has to be, I guess, limited at the very minimum at 40 degrees C. Okay, and then let's see how it will affect the results. So at 40 degrees C, you can notice that the vapor fraction is about 59.27%. Okay? You can also check the composition and then see that composition at stream 4 probably composition. Okay, good. So for stream 4, let me go back to worksheet of E101. At 40 degrees C, 59% of them will be in vapor phase, and in the vapor it will contain about 65% of hydrogen, while the acetone is still very high, close to 30%, and even we have around 5% of water. Okay, and the liquid that will be sent to the distillation column will have roughly about 51% of acetone and 41% of water. Okay, so the problem with this one is the cooling medium is cheap, very available easily. Okay, and the problem, we still have plenty of acetone that goes as a vapor. Okay, that means it has to be recovered in the absorber. That means we need big column, big water circulation. Okay, if you want to check the second option about the cooling medium, let's say now we use a chilled water. Chilled water, that means it contains some refrigeration, and let's say that the temperature now can be cooled even up until 10 degrees C. You will notice the obvious pros and cons. Okay, the pros or the advantage is now instead of about 57-59%, I have my vapor to be around 42%. And you check the composition. Out of those vapor, 90% of those is hydrogen, which is designed to be emitted, and only around 8.8% is acetone. So we already reduce load of the load for the absorber. Okay, and even if you want to keep decreasing the temperature, okay, now let's say we want to use a refrigerant, let's say using propane. It's gonna be more expensive for the utilities and the cooling media parts, but let's see if it gives us any. Okay, -30, vapor phase even become less. Now 99% already produced as hydrogen. Okay, and only less than 1% will be an acetone. We may eliminate the needs of absorber if we're working at this low temperature. Okay, but again, everything must have its own consequence. At -30 degrees C at close to 1.3 bar, you have to think about the risk of dose operation as well. For example, water. Okay, water at -30 degrees C at 1 bar, this condition very likely to start forming a solid phase, an ice. Okay, and you don't want that to happen in your piping, because it will plug the pipeline, it will plug the equipment, so it's gonna be quite challenging. Okay, so because we haven't evaluate the solid vapor liquid equilibrium, so now I will not use this option. So let me work in a safest or a safer condition. It's above the freezing point of water. So let's say now I'm going to keep 10 degrees. So now the cooling water cannot be used. The refrigerant will not be used. Instead, for the E101, I will use my chilled water to get into 10 degrees. Okay, I have my acetone has to be recovered from the. Okay, and it's a point of optimization. You can later play around with those number. Okay, so now it's already formed as a vapor liquid phase or mixed phase, so I can add my simple separator. Okay, let's go to the palette separator, the top left one. That's a two-phase separator. That means you have a two-phase means you have two products. You have the vapor product and you have your liquid product. Okay, and the difference with the other separation, three-phase separator, and you can probably even look by the flow sheet, you have now three outlets. Okay, you have the vapor, you have the light liquid, and you have the heavy liquid like oil and water as a two different liquid compounds. Okay, for this purpose I guess that it's not required. We only have one liquid and one vapor, so we can confirm the mass balance of the separator worksheet. Composition 5 and 6. A5, the vapor contains above 90% of hydrogen, which will be emitted or which will be used as a fuel in the utility section. The acetone is still about 8.8%, and 6 is our product, acetone and the other compounds that will be removed later. Okay, let's save it. Shift P so I know my pressure. Okay, let's connect it to my absorber. Okay, absorber, that's the icon. I told you before that we don't have any shortcut absorber. It has to be directly into rigorous absorber. and the idea is to recover the acetone using water. Okay, so let me define my water. Water composition is 100% of water. Let's say it's stored in a tank at ambient temperature and pressure. The flow rate we don't know at this point. Okay, we will optimize those numbers. So even for starter, I guess we can use ratio. We have about 2 ton of vapor. So if you also put as 2 ton per hour of liquid, that means our L per G will be close to 1. Okay, just as a starting point. Okay, see how will it result. And then you check again the pressure. It has to enter the absorber at the same pressure with the vapor. Okay, so I guess it will be logical for us to add a pump to enable the water from the tank then into the absorber. Okay, let's connect it. And for this pressure, what you have to define is only the duty or the pressure. And again, the pressure has to be matched with the vapor pressure. Okay, in that case, it's 1.3, or even again, we can use the set manipulator. Right, upstage in stream 5 actually has to be the button. Break the correct look. So the concept of absorber is you will send the liquid from the top of the stage and you will send the vapor from the bottom of the column. Okay, so it's safer to define it this way. Top stage inlet is the liquid, that's correct. Bottom stage inlet is the stream 5. Overhead vapor outlet, that's the gas discharge. Gas outlet, gas out, gas, and that's the gain. The stage, it has to be gas. Okay, we don't have any shortcut. The higher the absorber, that means we provide more contact area between liquid and vapor. That means the separation efficiency is likely to increase. Okay, but it's gonna be more costly. So again, it's a matter of optimization. So yes, we can make the absorber for now. Top stage pressure, it's provided at 1.3 bar, so we don't really have a lot of pressure left. So let me put it as 1.1, and the bottom is 1. Okay, it's optional, so we don't really have to provide anything, just done. Okay, before it can be run, still unconverged, but of course it's still unconverged. Even the inlet of the water has not been completely defined. Okay, in that case, we'll set the pressure, but using same concept. I want my pressure of this liquid to be identical with the pressure of my vapor. Okay, so pressure of stream 7 will match the pressure of stream. Pressure of stream 7 will be matched from the source object. Okay, once you do that, now it's green bar, dark blue, everything's ready. Okay, you can save it. And you can also open the absorber. Once you do that and go to the monitor, you probably notice that the degree of freedom is already 0 without having to specify anything. Okay, so different with the rigorous distillation, because we don't have any deboiler and we don't have any condenser in the absorber, so we can't define anything. Okay, if we put some number in the at spec over here, that will make it as a over specification. That's not a good thing. Okay, so once you provide the initial number, okay, so we use the mass rate to be close with the gas flow rate as a starting point, the stage to be 10 as a starting point. Now you just run it, and so they give you a green bar, which means it's okay. Okay, worksheet can check composition. Pure water to absorb 90% of hydrogen, and the result is now you get about 91% of hydrogen, and the acetone is recovered only slightly from about 8.8% reduced to about 5.5%. Okay, and the results, the bottom liquid out will give us about 90% of water and contain about 8% of acetone. Again, it's a matter of optimization. So is it red? Okay, you can also perform some quick calculation. For example, what will happen if you reduce or increase the amount of solvent? Okay, so from 2 ton per hour, if we reduce it to 1 ton per hour, obviously less amount of water sent to the column. That means less amount of water can absorb the recovered acetone. Okay, so logically the gas out now should contain a higher amount of acetone. Okay, let's try it. Let's prove it. Okay, that makes sense. Okay, so if you want to keep increasing this number, the function or the purpose of absorber becomes less and less obvious, because we still lose a lot amount of the acetone product. Okay, so maybe you wanna now increase it to 4 ton per hour. Okay, now my acetone is already close to 4%. Okay, keep increasing 10. Okay, now it's already less than 3%. Okay, so what would be the limit? Okay, can we go really high to about 100, for example? Okay, as you can see, if we provide 100 ton per hour, the amount of acetone in the gas out already 0. Everything is absorbed to the bottom, but the problem is maybe it's gonna be very costly. Why? Because now we will have a very big water circulation, even it's 5 times of our feed. Okay, so the rest of our process will not contain a lot of acetone or IPA. It will contain a lot of water. Okay, so that will be the problem, or that will be the challenge. So we can keep decreasing the number. At 50, it's still 0% of acetone, which is good. Okay, so let's keep doing this exercise. Okay, at about 30 ton per hour, I will still have a very small amount of acetone. Okay, this is a good case where we don't lose a lot of product, but again, we don't know at this point what's the consequence of sending this high amount of water into the process. Okay, because now obviously the discharge liquid, which will be combined with the discharge of the V100, will be mixed, sent to the separator column, and maybe that will have some effect to the distillation column. Again, we don't know for now, but let's keep it this way because we want to minimize the acetone loss. Again, I will give a disclaimer that this is still not optimized. Okay, it's just a first trial, and as in chemical process design, it will involve a lot of iteration before we get into the optimized number. Okay, so let's continue the rest of the simulation. Now we have to link the bottom outlet from the absorber T100 and the bottom from V100 to be sent to the distillation column. So let me add a mixer, and then you can also check the pressure and the temperature. Okay, the pressure is already the same. That is a good thing before it's sent to the mixer. And the temperature, okay, it's quite low, so let's us connect it and see how it will affect the mix stream. Okay, so the mix stream will be around 26.3 and 1.3 bar. Okay, so the pressure is already quite low before it's sent to the distillation column, so I guess it would be a good place where I put my second pump. Okay, so and then I will link it with my distillation column, and we always start with the shortcut. Okay, now the place is already very crowded, so I'm going to zoom out. Okay, yes, that's it for now. So I will rename the stream, open the pump, so the inlet would be stream 8 in my case. Just check your stream name. Okay, outlet, let's say that's as a pressurized separator feed, and then the energy to be my work of the pump 2, second pump. Okay, unknown duty, and you can use the principle that we talked in the previous video. When we want to use a pump, we have to define the duty or the delta P or the discharge pressure. In this case, we haven't identified those numbers, so we have to think about the pressure requirement in the distillation column. And again, remember the principle. It always starts from the top pressure, then the bottom pressure, then the feed pressure. And how to get into the top pressure, it is very helpful for you to use a dummy stream. Okay, so let me add another dummy stream over here. Double click, product dummy, for example. What's the composition? It's acetone 99.8. What about the rest? Okay, could it be hydrogen? I don't think so. Hydrogen will be emitted from the absorber, from the gas out. Will it be water or propanol? So acetone is the second lightest. The impurities of this component should be the third lightest or the second heaviest compound. Okay, so you have to think which one is lighter, propanol or water. The lighter one will come a long way with the product. In this case, propanol is lighter than water, so I will put it as 0.2%. Okay, so the composition is ready. Now I go back to my condition, unknown temperature, and then we have to think about the phase itself. We want to produce acetone liquid. That means the vapor fraction would be 0. This is a saturated liquid. And think about the pressure top. I want to use my cheapest cooling medium. In this case, it is cooling water with the temperature range between 30 to 40 degrees C. So I'll give another 15 degrees C for delta T log mean temperature difference in the heat exchanger. So let's keep the product to be 45 degrees C. And once you do that, you will realize that the bubble pressure for those conditions would be at around 0.68 bar. And this is not really a good number because it's already in a vacuum condition. Okay, in a vacuum condition, it's gonna be costly, is hard to control. We have to install an ejector or a vacuum pump. So again, this is, I think, quite similar to the second distillation in the DME case, where we will compromise or we will check another options. Okay, I will not push the temperature to be at 45 degrees C. Now I want my pressure to be as mild as possible. That means it's slightly above atmospheric. It's still not vacuum, but it's not a high pressure. So let's say, what if I perform at 1.2 bar? The bubble temperature for this pressure now will be at around 61.1 degrees C, and that is perfectly okay because that still can be condensed using a cooling medium. Okay, even we have a higher driving force in the condenser now. So I will use this number, that is my condenser pressure. My reboiler pressure will be 1.2 plus delta P, let's say 1.4, and then the feed pressure will be above those 1.4 bar. Okay, so let's say to round it up, that means I don't really need a high pressure. Let's just pump it to 2 bar, and then I will send it to my distillation column. Okay, let's name it properly. QC1 for the condenser, QR1 for the reboiler, distillate will be DIST1, bottom one BOT1. Okay, let me arrange the stream to look clearer. Unknown key components, then you just go to the parameters. Okay, to help you fill in this information, I will open the feed composition. Okay, so what is our product? At the distillate, I want to get high purity of acetone with a small impurities of IPA. Okay, in that case, my heavy key in distillate will be IPA. And the number is already explained in the product dummy. It will be around 0.002 to get 99.8% of acetone. Okay, light key in bottom, you have to think what will be in the bottom stream. Obviously, most of them would be water and IPA. Okay, we will not have hydrogen. We may have a slight amount of acetone into the bottom. We can't choose the water because that will be the heavy key in bottom. It's not the light key. Okay, can we choose the IPA? No, we can't, because we can't use the same component to be in both key components. So that leaves us with the next logical choice, that it would be an acetone. Okay, we will let a small amount of acetone to go into the bottom. Let's say it's 0.001 or 0.1%. And then check the pressure. Let me save it. Okay, 1.2 bar based on the product dummy exercise, 1.4 bar. Okay, now HYSYS gives us a warning that they can't find an equilibrium at this setting or condition. Specifically, HYSYS unable to find the top tray temperature at specified conditions. So we have to think about the possible causes. Okay, tray temperature, that tells you that the problem is in the top of the distillation, not at the bottom but at the top. That means the cause probably will come from the light component. Okay, and if we look at the material stream, what is the light component? The light component would be acetone. Okay, water is heavy, so that may not be the problem. Propanol is heavy and it's actually quite small. Okay, how about hydrogen? It seems that we don't have any hydrogen anymore, but be careful because it is expressed in mole fraction. What happens now if I change it to my mole flow? You will notice that we still have a small amount of hydrogen sent into the distillation column, and you have to imagine how would be the consequence when those small amount of hydrogen has to be condensed. Okay, why? Because we choose a top product phase as a liquid. Okay, so we want to liquefy a hydrogen, which is a very hard thing to do. It's gonna require a very cold temperature. Okay, So at least there are two options to fix this. The first one is to introduce the splitter, which I'm going to do next. But I also want to show you that it may comes from our guess or our selection on the absorber part. Okay, so I will put it over here and then put it somewhere here. Okay. Remember when we play around with the amount of the solvent going into the stream. Okay, it's 30 ton per hour to get almost free acetone at the top of the absorber. And we also probably notice that the amount of the water sent into the process is very big. Okay, it's even the flow rate is even higher than the flow rate of our feed streams. Okay, so that may also be the case. We can check the consequence. Let's say we revert it back to our initial guess. So I will revert it back to 3, reduce it by 10 by an order of magnitude, and you probably notice over here that now the shortcut distillation actually can be solved. Okay, yes, we lose a lot of acetone, but a less amount of water sent to the system, and it actually helps us to converge into the shortcut distillation. Okay, so minimum reflux ratio is 0.85. I'm going to give around 20% extra, so another 0.17, I guess. So just to round it up, 1.1. See the performance. Okay, now you notice some problem. Okay, you notice some problem. It can be done in 28 number of stages, but the temperature of the condenser will be very cold at about 19 degrees C, whereas you previously set the pressure of this 1.2 bar top stream from this 1.2 bar product dummy stream at the required composition. And we expect the temperature to be about 61 degrees C, but now HYSYS think that's not the correct number. The correct number should be around 19 degrees C. And it's maybe confusing for you, but when we look at the distillate, okay, we can't even achieve the purity of the acetone. Okay, it's not 99.8%. Why? Because we still have a very small amount of hydrogen. Okay, that's why it's very, very problematic for us to have a very light compound such as hydrogen going into the distillation column. Okay, so that's why I want to introduce the splitter. Okay, let's add a splitter. Okay, component splitter, that's the icon. So let me put it somewhere over here. Again, this is just a simulation technique, okay? And the idea is to remove those small impurities of hydrogen in this splitter that will be sent to the actual distillation column, okay? So let's connect those pressurized separator feed. Okay, then let's say that would be vapor, vape splitter. Oh, well, it's not really as vapor, so let's put it as top splitter and bottom splitter. Okay, the energy stream, we can also link it. Okay, I will go to the split first to follow the instruction unknown splits. Okay, so I will go into the split first. Later we will define the condition of the splitter. Do we want to use an equal temperature or do we want to equalize the pressure? We have a lot of manipulation can be done using this splitter column. Okay, so let me go to the splitter first. we have 4 compounds, so the idea is we want to split the hydrogen to be sent to the top of the splitter, while the other 3 compounds to be sent to the bottom splitter. And this bottom splitter will be sent further into the distillation column, free of hydrogen. Okay, so you just have to check. You see that we have option set to 1 fraction and set to 0 split fractions. Okay, in this case, you have to think, where do you want to get your propanol? I want to get my propanol at my bottom splitter, okay, free of hydrogen. That's, I choose the bottom splitter to be set to 1. Water, where do you want your water? I want my water to be in bottom splitter, free of hydrogen. Acetone, same thing. So the only difference is the hydrogen. I want my hydrogen to be 1 at the top splitter. Okay, and then after you define the split, you go to the parameter. You will notice that you will have to define the pressure and the temperature of this splitter. Okay, let's say equalize the all stream pressure. Okay, because we don't really want to manipulate the pressure, we just want to manipulate the composition. Okay, pressure 2 bar, 2 bar, 2 bar. Temperature, it's still empty. Okay, calculate equal temperature. Again, we don't want to mess with the temperature, we just want to separate the hydrogen. Okay, let me save it. So now when I go to the splitter and I check the composition, so the only difference is now I don't have the hydrogen at my bottom splitter because it's separated at the top splitter. Okay, I'll save it and I will send it to my shortcut column. I will not delete the previous shortcut distillation column, just as a comparison purpose. Okay, maybe it will help us somewhere along the line. Okay, so I will connect with my bottom splitter. Okay, now the name has to be selected carefully. We can't duplicate the name in the previous shortcut column. Okay, let's say now that's the top one. Or vapor, I guess. Vapor, oh sorry, that's the condenser duty. So that's Q con 1. Q rep 1. This is still the first distillation column. That's why I still keep the 1 in the stream name. Okay, that's the product 1 because that is our acetone product, and the bottom is bottom 1. Okay, you can use the different name, obviously, just be consistent. Okay, that's the important thing. Okay, unknown key component, we've already done this exercise before. The heavy key in distillate would be the IPA, and that would be the acetone. Put the same number with the previous shortcut column. Okay, the pressure, let's keep using the same pressure. Okay, minimum reflux, it's already 1.5, so give another 20%, would be around 1.8, I guess. Okay, then check the performance, and I will put it side by side, or okay, with the previous column. Okay, so you will notice that after we separate the hydrogen, now we need more tray. Okay, it's fine, but the important thing now, the temperature now match our estimation. Okay, match our dummy prediction. Instead of working at a very cold temperature where you can't use a cooling water, okay, you need to use a chill water at least for this one. Now you can use a cooling water because it's already at 61 degrees C. Reboiler doesn't have any problem, again, because the problem is at the top. Okay, check the composition. Okay, product 1, Okay, now it matched our product specification of 99.8%. It's 99.77%. So I hope it helps you the understanding of why we need the splitter in this simulation. It's to remove the very light compound in the hydrogen. In practice, we don't really have this column in the plan, but the process itself can be done in in several locations. Okay, for example, when we have a distillation column, usually we will have an overhead condenser before it's sent to the reflux drum. And the hydrogen, if we maintain the temperature at about 61 degrees C at 1.2 bar, the hydrogen will not be condensed. That's why the hydrogen will still be emitted as a gas from the overhead reflux drum condenser column. So it's a simulation technique, but it's not impossible task, you know. So actually we can do that in the plan to separate those gas hydrogen. Okay, so let me continue with the rest of the simulation for now. So I'm still going to keep the current setting. So the last time I checked it, I reverted back to 3 ton per hour. Okay, and that makes my acetone loss to be quite high at about 4 point less than 5%. Okay, let us finish the loop first, and then we can play around with the number. Or even if you want, so let me zoom out the screen again because I need more space. To get a lower number of acetone loss, you can also play around with the amount of stage in the absorber. Okay, we haven't checked the results on that one. So if it's only 10 stages, 10 stages is like 5 to 6 meter of column. It's quite small. The acetone loss would be at around 4.8%. So let's just try. If we double that amount, it's still doable. A column with 10 to 12 meter height with the same water inlet. Okay. Can we? Okay, pressure is still the same. Okay. Okay, you notice that the acetone reduces only slightly. Okay. It reduces only slightly by about 0.2%, I guess. So it's helpful, but not really helpful. Okay, and it still allows us to complete the rest of our simulation. So if you want to keep as 20 stages, that's also fine. Okay, so next I will send it to my second distillation column. Okay, which is coming from the bottom of the first distillation column. And again, to check the pressure. The pressure already at 1.4 bar, so maybe you will need another pump over here. Okay, again, in practice, you will have a lot of pressure and elevation, so it's logical to have a pump. Okay, so what's the name from bottom one? Work of my third pump. It is the pressurized separator 2 feet. Okay, the pressure, again, the same principle will be matched with the requirement for the second distillation column. Okay, so I will add my second distillation column, and I will add my dummy stream. Okay, just in case I need my dummy stream. Okay, so think about what will happen in the next distillation column. You have water, you have IPA, you have small amount of acetone. So the idea is to remove the water from the system, where you recover the propanol and the acetone back into the mixer. Okay, so you want to revert back the propanol and the acetone back into the process. Okay, so you want to reduce the water at the top to be as small as possible. So that means at the top you want to get as much as IPA as possible. Okay, is that doable? Let's check. So can I get 99% of acetone with only 10% of water? But remember, okay, remember that propanol and water forms azeotrope condition. Okay, so it's not gonna be as simple as the first distillation. So let's try it. Can I get, okay, you see that at 99% of IPA at saturated liquid condition at 45 degrees C, we require another vacuum condition. And again, we don't want to do that. So I'm going to compromise the temperature. We'll use the mildest pressure. Another 1.2 bar, slightly above atmospheric. It's atmospheric, but prevent any vacuum condition. Okay, 85 degrees C, that's very doable. So I guess we will have a similar pressure profile in the second distillation column, 1.2, 1.4, and 2 bar at the feed. Okay, 2 bar at the feed. So let's put it to make it easier to remember. That's the recycle dummy. Okay, connect it, press sep to feed. Okay, so now the name would be as consistent as possible, qcon2, qrep2. That's my distillate 2. That's my bottom 2. Okay, unknown key component. So again, perform the same exercise. What do you want to get? I want to get at the bottom mostly water. Okay, so that's the heavy key in bottom. The light key in bottom will be the next lighter compound from water, which will be the IPA. Okay, so let's say you want to put 0.01, for example. So you allow 0.1% of IPA to be sent to the bottom with water. And how about the heavy key in distillate? The heavy key in distillate, we don't have a hydrogen anymore. Acetone, it can be, okay, acetone cannot be the heavy key in distillate because the main compound in the distillate now would be IPA. Okay, so the logical thing is our heavy key in distillate has to be heavier than the main compound in the top. The only heavier compound than IPA is water. Okay, so let's put a small number first. Fill in the other composition. A minimum reflux ratio less than 0 has been calculated for operation T103. You check that the minimum reflux ratio is close to -2. So that's not possible. Again, we have to find the causes and then fix it. Okay, how? Use your judgment. Okay, we can check the feed composition first. Okay, what are we separating? We want to separate mostly water. Okay, so again, water in the second distillation column will comes at more than 90%. Okay, that's even after reducing the water solvent in the absorber. Imagine if we haven't decreased those number, we still keep 30 ton per hour. This water in the distillation column would be even larger. Okay, maybe close to 95 or even 98, 99%. Okay, so it's gonna be very, very hard to perform a distillation at those high water content. Okay, and also I want to remind you that we are dealing with a azeotrope condition. Okay, so check where is our location at this azeotropic chart. Okay, so we send the feed of the second distillation column at 90% of water, at 10% of propanol. That means it's gonna be around here, 0.9 of propanol and close to 90% of water. Okay, in that case, it's impossible to get two pure compounds at the top and at the bottom, because now we are working at the left window. So I will say this is the left window before the azeotropic condition, and this is the right window after the azeotropic condition. We can only work in this left window, okay, because that is our feed location, 10% or 9% of propanol. That means in the distillation column, it's possible to get pure water. Okay, it's possible to get pure water because it is in the same left window. Okay, pure water with very small amount of IPA, but it is impossible to get almost pure IPA. It will be limited below the azeotropic condition. Okay, so check and use those information to your shortcut column. Can I do it whether to check your recent input? Okay, is it possible to have 0.001 of water in the distillate? Okay, my pure propanol, okay, obviously this is wrong one. There is no way I will get pure propanol only with 0.1% of water, because that will be in the right window. Okay, so that's where the problem is. Okay, delete it for now. Check the top one. I want to get my bottom product as water with 0.1% of propanol. Very small amount of propanol with water. Okay, that's doable because it's in the same left window, and you can see that the range between bubble and dew curve is very large in this left window instead in the right window. So it's easier to perform the distillation in the left window. So let's change the number now. So let me go back to mole fraction. Okay, what happened now? View table. Okay, check where is the azeotrope condition. Okay, I think this is the azeotrope condition. It's gonna be at around 0.68 mole% of propanol. So I can get pure propanol. The maximum would be close to or below this 68%. Okay, so just to make it safe, let's say I will allow 40% of water to be at my recycle stream. So let's try 0.4. Okay, done. So that can be solved, but again, back to our fundamental. Use your judgment, use your engineering sense. Now we're working at the left window of those azeotropic condition. So now it can be done. Okay, 0.824, give another 20% allowance. Let's say it's 1.1. Okay, I'll save it. Okay, so check the composition now. Okay, I get my almost pure water to be emitted to the wastewater treatment plant, and this is my recycle stream, where I will recycle the top of the feed back into my system. Okay, I will save it, and then check the pressure, 1.2 bar, I will send it back to 2.2 bar. So that means I will have to add a pump. Where is the pump? Okay, I will have a pump and I will have a recycle stream. Okay, and then I will go to the flow sheet and then flip horizontal to make it easier to be red. Okay, and then I will connect everything. Shift, okay, press control, but I will not link it. I leave it at that point for now. Okay, add the energy stream. Okay, if you want to change the name to be consistent, we have work pump, so I guess we have to be consistent. Work pump 4. The pressure will have to be the same with the pressure of this press fit stream. So let's say I want to use another set just in case. Okay, now the pressure of stream 9 will be matched with the pressure of pressurized fit. Target variable is stream 9 pressure. It will have to match the pressurized fit. Okay, check the number 2.2, 2.2. It's okay. One more thing, so I'll save it. It's good when once we have a more complex system or simulation, we use a lot of setting. Okay, that's why once the number is adjusted, everything will be adjusted accordingly. Okay, if you need one example, for example, now we are guessing the number of this water in the stream to be 3 ton per hour. Okay, but you can imagine once this recycle stream is combined into the mixer, it will add the mass flow rate of the rest of the stream. Okay, instead of 20, maybe it's gonna be 22 point something ton per hour, and that will obviously affects the equilibrium in the absorber. So it's up to you. If you don't change the value of the flow rate over here, so just keep it as 3, those number will not change even after you change or after you combine with the mixer. Okay, so you will change the L per G setting and absorber, and obviously that will affect the rest of the simulation, and that is not preferable. That's why I want to add another set in this one. So I want to keep my L per G in the absorber to be consistent. Okay, so it's 3 ton per hour. Let's say now my water solvent will be fixed with the amount of let's say in the stream 4 or stream 5. Okay, I guess stream 5 will be a good thing. So the ratio now would be around 1.5. Okay, 3 per 2. Okay, so the multiplier, okay, the target variable would be our flow rate of the water solvent. Okay, so my water solvent, that's the mass flow rate, mass flow. Okay, select. My mass flow will be affected by the stream 5. Okay, and the number now is roughly 1.5. Okay, so 1.5 times 2 will be close to 3. Okay, so every time the stream change, now the water content flow rate will change as well. That will be coming from stream 5. Okay, then you delete the mass flow because we don't need those information anymore. Okay, so what's the problem now? 1.8. Okay, everything's good. I hope now we're ready to mix the mixer. Okay, stream 10 to the mixer. Okay, save it. Sometimes it gives us trouble. Okay, now the absorber cannot work. What's the problem? 2.3, 3.5, so that already match. Run. Stream 7 doesn't have enough information. Okay. I guess I will break my connection first. Again, usually the problem comes with the recycle. Okay, once you break it, everything now looks good again. So, what's the problem with the recycle? Okay, the number is not correct, so let me break the connection first. Okay, let me think. Let me ignore this one. So I will set my pressure now manually 2.2. Okay, maybe too much setting. Save it. Okay, let's try. Second try. Let's try to connect it. Unable to find bottom tray temperature at T102. Okay, that's the problem. Okay, let me check the composition. Okay, a lot of water and acetone. Okay, I guess that's still not a problem. So let me add the number 1.8. Okay, that's done. Okay, I think now it's fixed everything. Second column, okay. Composition 99. Okay, I think it looks good. Everything looks good, and we're finished with the heat and material balance. Okay, now we just have to check about our products. Our products now is 99.8%, but instead of 10 ton per hour, it's 16.13 ton per hour. So we have to refine the amount of it. Okay, let's save it. So let's try to manipulate the fit now. Okay, so from 20 ton per hour now I have to reduce it by about 5/8, I guess. 300 something. Okay, getting there. 280. Getting there. 250. Okay, too small. 265. Okay, I guess that's quite good for now. 264. Yep, perfect. So I guess that will be it. We finished the heat and material balance. We get 10 ton per hour acetone at 99.8%. So you see that the simulation now becomes more complex, but I hope you still understand the fundamental and also the technique in HYSYS. That's why we need a lot of splitter, we need a lot of set, so that once you change the number in the feed, the number in the water solvent will be adjusted automatically. So imagine if you don't have a lot of this setting, you change the feed and then you have to change the solvent in next step, and it will give you a lot of trouble and inconsistency and even some error. So think about where you have to put the set. Okay, so I guess that's it for this video. So I'll see you in the next video to complete the rigorous simulation. Okay, I'll install another PFR over here, I will install another rigorous distillation over here, and I will install another azeotropic rigorous distillation over here. Okay, see you in the class and next video.